some C code to do the actual. So one of the interesting things about the Flash player is that it's sort of more like the browser in that it's kind of event-driven, whereas your typical C application is you've got your one main function, it runs forever. Again, the more sort of event-based case on the right, you respond to a mouse click and do a little bit of work and kind of return back up. So if you kind of naively converted a C application to a Flash application, you'd have main. It would run for 15 seconds, hit flashes, the script has been running too long, timeout, and you would never see anything. So we have basically a path that takes synchronous C methods. So here's a very simple example of a synchronous C method, and turns it into an ActionScript class that is more or less a finite state machine that can be sort of fed cycles and will iterate a state each time. So you can effectively interrupt your C program at a more or less arbitrary time, and that allows you to run a long-running application without hitting the 15-second timeout. It also lets you do things like respond to keyboard events, which aren't going to get processed in Flash's event loop unless you sort of return all the way back up. So you can do things like you have your finite state machine and you hook it up to like a timer that's running 1,000 times a second, and it just sort of iterates on the finite state machine every time it gets hit. And so again, basically each function is a finite state machine that roughly is equivalent to an ActionScript class with like a state member variable in it and a big switch statement. And the sort of local registers, I told you there were the sort of 32 general purpose integer and float registers. Those are actually local to each finite state machine. So I don't know, conceptually it's like register windows or something along those lines. And so invoking a function is more or less equivalent to instantiating one of these finite state machine objects in this world. And there are cases where we can establish that we definitely aren't going to need to sort of be able to suspend and resume this particular function. And in that case, we won't go to all the work to do the finite state machine, as it has a reasonable amount of overhead. And so, you know, finite state machine instances of function invocations are more or less conceptually equivalent to call frames. So there's sort of a chain of those at any given time. And again, typically, in a large C application, those will be given time slices off of a timer object to give the Flash runtime the ability to respond to events and so forth. But a kind of neat side effect of this is you can just have multiple chains of finite state machines and just kind of, you know, round robin between them and sort of simulate threads that way, despite the fact the Flash virtual, you can write multi-threaded C code on the Flash player, but not multi-threaded ActionScript. So again, the C standard library itself is ported, but the basic system services like very low-level open, not fopen, but open, very low-level memory management, not malloc, but sbreak. Those things are written in primarily ActionScript with a little bit of C glue code, and again, the bulk of the C standard library is ported. So you're probably wondering about performance. And it's surprisingly good. So this is Visual Studio 2008 optimized version of the SciMark II C version of their benchmark. And this is a log scale, just to be clear. And here's Flash Player X running the same benchmarks. And you know, some of them are quite good. This is better than 50% of fully optimized native code, which is pretty good. And I think the worst case is still, I mean, yeah, it's pretty far off, but I mean, we're running C code in the Flash player. So this is a little bit broader view here. So this is SciMark II again, converted to ActionScript fairly naively. Basically, it's syntactic translation, and it's running it on the machine I used at about 12 megaflops. The FlaCified C version is running at about 304. The C# version, which was again basically syntactically translated from the Java variant of SciMark II, is actually only slightly faster than the C version, which is kind of interesting. And the C version running on CLR is, again, only kind of incrementally faster. And once we get to Java, it's, twice as fast, or about, and then maybe about twice as fast again here going to real native. And I've got a little performance demo, too. The bar charts are nice, but run a little cheater app here to run as a sound even. So this is an Air application. And this is basically the Quake video game running on we all remember having to do this with Quake. Turn the brightness up. Hopefully we can see that a little better, I don't know. Okay. So this is the Quake runtime, the Quake video game, ported using the tooling and running on basically shipping Air 1.1, which is more or less the Flash 9 runtime with the memory optimizations that I sort of touched on earlier. And it's running, I don't know, 30-ish frames per second or something along those lines. Obviously totally playable, 800 by 600. And this is the pure C code, so this isn't even using the nifty assembly stuff the ID guys did originally. And it's all, it's all these finite state machines for the asynchronicity too. So it's got kind of a lot working against it, and yet the performance is still pretty good. So coming to a browser near you.
Is it on your blog site?
No, there might be some licensing issues with trying to give away Quake, although it would be cool. So the fast memory operations that I alluded to essentially let you take that byte array, and again, we're using a monolithic single byte array as RAM, and kind of bless it as I'm the most important byte array in the room. And once you've done that with single opcodes, you can load and store to and from that byte array. And those, since there's only this one byte array that we know of ahead of time, we can actually JIT these accesses one-to-one with, the sort of read opcode and an actual move instruction on x86. So it's very, very fast. Obviously, it has to do range checking to make sure you don't, escape the security sandbox. But in sort of real code, you see a lot of access EBP plus this, and then plus this, and then plus that, looking at arguments and doing spills and all sorts of stuff. And you can actually basically range check whole series of those. So it's not even a range check per access. And it's actually quite fast. It's only a couple of percent, 2 or 3%, something like that, overhead over just plain native memory accesses.